Alright, so in this video I am going to talk about the chemical properties of lipids which contain fats, including fatty acids and triglycerides, as well as cholesterol. Okay, so first I'm going to talk about fatty acids, and then I am going to talk about triglycerides, and after that I will talk about cholesterols. So I don't think I meant for this to be here. This is cholesterol actually. So I am just going to get rid of that because I have that pasted somewhere else in here. Let me go ahead and repaste that because I think it got covered up. So that was this one. Okay. All right, back on track. All right, so the first thing we want to talk about in fatty acids is the difference between saturated and unsaturated. So when you look at the nutrition facts on your food labels, you will probably see that it says it has some amount of saturated fat and some amount of unsaturated fat. So the difference between these two is a double bond. So unsaturated fats have a double bond somewhere inside of the hydrocarbon chain of the fatty acid. Both of them have the carboxylic acid at one end of it. That's why it's called a fatty acid, because it has this carboxylic acid at one end of it, with the rest being just a hydrocarbon chain. And the unsaturated has this double bond in it. And it can have multiple double bonds, but unsaturated, so monounsaturated in fact, monounsat, I'll just call it monounsat, has a single double bond, and unsaturated has more than one double bond. And that will give these different physical properties. And the reason that this is called the saturated and unsaturated is because we're talking about the saturation of hydrogens in the hydrocarbon chain. So when you have a double bond, that reduces the number of carbon or hydrogens you have in the hydrocarbon chain by 2, so it's unsaturated of hydrogen. So if you have no double bonds, then you are saturated with hydrogens. The other thing that we need to know just to get started here is the length of fat chains. So if most people have heard about saturated and unsaturated fats, and probably a few less people know that fats come in these different chain sizes. So each of these little gray spots is a carbon, the little white ones are hydrogens. And so you can see with C4 we have 1, 2, 3, 4 carbons, and then it increases by 2 from there. I mean, you can have an odd number, but usually we use even-numbered fatty acid chains in our diet. So these down here that have 4 and 6 carbons are the small chain fatty acids. And then what you find in things like your coconut oil are your medium chain fatty acids, which are the 8 carbon and 10 carbon, and then your large chain fatty acids, which are the sorts of things you will find in, well, what we consider fat. You know, when you eat a piece of meat and you have fat in it, they are these large chain fatty acids, and these different chain lengths give this different physical properties. And so, for instance, up here with capric acid, and each one of these has its own name with it. So capric acid is the version with 10 carbons in it. We see that its melting point is 32 degrees Celsius. And then we move up to 12, 14, 16, 18, and 20 carbons in our hydrocarbon chain, and we see that the melting point is now 76 Celsius, which for my American friends, my fellow Americans rather, who use Fahrenheit rather than Celsius, this would be quite hot. I don't know exactly what it would be in Fahrenheit, but this would be quite high temperature for it to melt. So things like stearic acid and arachidic acid are going to be solids at room temperature. When you get down to these medium and small chains, you start seeing that these are liquids at room temperature. If you've ever ordered MCT oil or bought MCT oil because of the health benefits, that's medium chain triglycerides. So they're triglycerides made out of these medium chain fatty acids. I'll get into triglycerides here in a little bit, but these are the medium chain. So the melting temperature increases as chain length increases. And that's because, as I talked about in the general chemistry preliminaries, when you have longer and longer chains, you start getting those van der Waals forces. So van der Waals. So say if you have a 1, 2, 3, 4, 5, 6 chain hydrocarbon, it's going to have one melting temperature, and then if you have a 1, 2, 3, 4, 5, 6, 7, 8 chain hydrocarbon, there's going to be more van der Waals forces going on between these two, and so the melting temperature will increase. And the same goes for when your fatty acids. These have this carboxylic acid on the end of it, but they still obey those same rules as far as the van der Waals forces between them. And so another way that you can affect the melting temperature of fatty acids is by introducing these double bonds in them, making them unsaturated fats. And so as you put more and more double bonds in it, you see that the melting temperature goes down. So when it's saturated like this, the melting temperature of stearic acid, which here has it as 70, up here at 69, so it's in that 70 degrees Celsius range. Then adding a single double bond into it, the melting temperature is reduced quite substantially. Adding another double bond reduces it even more, and even more with 3 double bonds. And the reason for this is that, as you see in these hydrocarbon chains, they kind of stack into each other, and that's what allows you to get the full benefit of these van der Waals forces. And so, you know, having more carbons in the chain allows more van der Waals forces. But if you have a double bond like that, then you see over here that this causes this sort of curvature, this bend in the chain, and so you don't get this nice stacking on top of each other. These unsaturated fatty acids don't stack on top of each other as nice, so they move past each other and they wiggle around a lot more, and so that makes them much more liquidy. And so when talking about unsaturated fats, you've likely heard of something called omega-3 fatty acids, omega-3, and this is the omega-3 symbol. That's the Greek letter omega. And so the reason that it's called that is because we're 1, 2, 3 away from the end, and then we have this unsaturation right here, that making this an omega-3 fatty acid. So the three types of omega-3s that we obtain from our diet are the alpha-linolenic acid, the EPA, and the DHA, which if you've ordered fish oil, you've probably seen the EPA and DHA contents on the nutrition label. And so they all have this omega-3 unsaturation here, but they all differ in chain length and where their other unsaturation sites are located in the chain. And so all three of these are the omega-3 fatty acids that we obtain from our diet. And when we get into the biochemistry, I will show that humans do actually produce EPA and DHA. These are called, these fatty acids are said to be needed from our diet, but we can actually produce them from the alpha-linolenic acid. And so alpha-linolenic acid is the only one that we actually need to get from our diet. The production of these other two from alpha-linolenic acid is not that high, so it's better to get these from our diet than it is to try and just only have alpha-linolenic acid. But I'm just saying that we do have the biochemistry necessary for making the DHA and EPA from alpha-linolenic acid. And so that you see all these unsaturated points, which is why fish oil is always in liquid form, whereas something like butter or something, which is saturated fat, is not in liquid form, because these have these unsaturated points. Okay, and so the next thing we can talk about is we take our fatty acids and we combine them together using glycerol or glyceride. And to do that, so once again, these R's just tell you that there could be, some chain going off of this that's just an arbitrary number of carbons. And so we're just interested in this right here. And so what we can actually see here is if we have our glycerol here, and we're interested in this over here. So we have our glycerol and we have our fatty acid. Once again, this R is some chain of carbons, and this is the carboxylic acid on the end of it. And so what happens is a reaction called esterification, where this oxygen right here will attack that carbon there. Once again, that electronegativity comes into play, where we have the partial negative here, the partial positive on the carbon, we have partial negative here, and so I'll show the mechanism over here. And so we have R with our OH, and then we have R with our carboxylic acid. And so this is going to attack this on that carbon. It's going to shift those electrons up there. And so we end up with, we'll call this R1 and R2, just to show that they're from different molecules. And so we have our this carbon right here, and so we have something like this as an intermediate, and this is going to have a positive, and this is going to have a negative. So then what happens is these electrons will collapse down on there, which makes this a double bond. But we know that carbon only ever wants to have 4 bonds, so something else has to go. And the thing that's going to go is this right here, this OH. So just to keep it a nice concerted mechanism, we can have that bond switch over to this, which then goes to that. So then we end up with R1 going to that oxygen there, which then goes to this carbon, which then we can have it look like that. And so that's how we end up with, so in this instance, we this was the was what this species was over here, and so we end up having this CH end up bound onto here, and we lose a water from this, so water will come off from this, which was from this OH here plus this H here becomes our water. And that's how you can add some fatty acid chain onto. So I was kind of doing this in reverse. You can go in the other direction, which then adds a water to it, and which is what they show right here. And then you free your glycerol and get your fatty acids freed from the glycerol. But I was showing it in this direction here. And so we're taking our fatty acids and our glycerol and turning it into a triglyceride, which I show down here. So we see our glycerol here in blue, and then they show the what used to be the carboxylic acids here in red, but now that we have a C bound to it instead of an H, this becomes an ester bond. And so we see we have 3 fatty acids on it, which is why it's called a tri, that has 3, and then glyceride because it's bound to glycerol. So triglyceride has 3. And then we can also have something like this, where our glycerol is bound to just 2 fatty acids. And if we ignore this up here for just a minute, we can call this a diglyceride. And of course, we could also have just a single fatty acid, which we would then call a monoglyceride. And when you have these mono and diglycerides, then you have this, you have the other OH group not bound to a fatty acid, which then means you can put other things on it. And one of the things that we often see on diglycerides in biochemistry are phosphates. So that would make it a phospholipid. And then on the phosphate, you can add other things. There's a whole number of different things that you can add onto here, and they end up having different functions, which, as we get further into the biochemistry, once we start going into how these molecules are handled in the body, then we'll talk about the various sorts of modifications that we can have on this other oxygen on our glycerol. And so those are the triglyceride, diglyceride, and monoglyceride are the three forms of fat that we get from our diet. And this is the way that fat is stored inside of us as well. Okay, then I'm not going to go too deep into this, but just so that you're aware, there is another form of fat, and this is found almost exclusively in brain cells, which you can, if you know brain terminology, you can see cerebroside, cerebral like the cerebrum, and sphingomyelin like the myelin sheath on neurons. So, and ceramide like cerebrum again. So these are all things built off of this sphingosine, which we humans can generate using regular fatty acids. So this is Palmitoyl Coa. I'm not going to go too deep into this, but this is just if we have our carboxylic acid, and then we just add something called acetyl CoA. So, and they often show up with the S there because that's actually a sulfur on the end of it, and that acts similar to the oxygen on here, and that will attack there, and then you end up getting your CoA on there, so you end up with a sulfur down there, and then CoA is just some other molecule, and we will encounter that a lot as we get into biochemistry. But I just wanted to show that this sphingosine and then all the other derivatives of it are things that is a type of fatty acid that we derive in our body. So we take the fatty acid, we attach that CoA, and then through some enzymatic mechanisms here, we attach a serine to it, and we end up getting this sphingosine. Like I said, I'll go into that more once we get into the biochemistry further down the line. All right, so now we can shift our attention away from fats back over to cholesterols and their various derivatives. So this is the molecule that we call just cholesterol. When you see cholesterol on your nutrition facts, this is the molecule that we're talking about. And you can see on here that besides this OH here, this is all hydrocarbons. So it's quite nonpolar. It's quite hydrophobic. It doesn't dissolve well in water. And you can see, so one thing to notice is on cholesterols, you always have this 4-ring structure here. So these 3 6-member rings, and then this 5-member ring, and then the various derivatives of cholesterol have different substitutions in these areas. So you can see that estrogen, which is a hormone that is mostly found in women, you see that you still have these 3 6-member rings, and then the 1 5-member ring on all of them. But this hydrocarbon chain up here is substituted out for some oxygens, and this right here, we have these double bonds added to this 6-carbon ring, so that gives it different properties as well. And then testosterone, the same thing. So we have the OH here substituted for a double bond oxygen. We have this hydrocarbon chain substituted for an OH, and what these different substitutions will do is make it so that these bind to receptors, different receptors, so hormone receptors in our cells, which once again, once we get into more biochemistry, I'll cover that in more detail. But right now, it suffices just to notice that all of these have these different substitutions on it. And then another molecule that we make in our body using cholesterol is bile salt. So cholic acid is just one type of bile salt. There are numerous types of bile salts, but we use cholesterol to make bile salts, which bile salts are used to emulsify fat that we eat. So when it's in our small intestine, these bile salts are released, and that helps emulsify the fat. And one thing to notice here is all these OHs that are on it. In this projection here, in this representation, these are all pointing into the screen. And so we end up with a molecule that actually has a net overall partial charge that is pointing into the screen in this representation. And what that does, that's how it can actually do the emulsification, which up here we see. So fat, as you probably know, doesn't mix well with water. So when fat is in a water solution, it likes to sort of bunch up like this into large fat globules. And so in the small intestine, you release the bile salt. Like I said, we have those 3 hydroxyl groups that give this an overall partial charge in this direction. And so this fatty part can actually associate with these small parts of the fat globule, and this part can this part can go into the H2O, and so you end up with these sort of forming this shield around the fat globules, which allows it to sort of dissolve in the water more, because these fat globules become smaller than what we have here. And that's what emulsification is it's using this differential in hydrophobicity and hydrophilicity so that you can actually somewhat dissolve these in water. And there's a similar mechanism when we talk about soap. And soap is basically just fats that we then add lye or sodium hydroxide to, and that actually it takes the glycerin off and gives us fats. But in this case, so that's our hydrocarbon chain, instead of having the fatty acid like this, instead we end up with this with the negative charge, and it'll have a sodium positive charge. And so this charge will actually interact with the water, and the hydrocarbon chain, which goes off there, will interact with fats and grease. So we end up with, these are called Micelles. So the hydrocarbon chain is interacting with the hydrophobic grease, while the head of this molecule is interacting with the water. And so that's how when you add soap to greasy water, this can lift grease off of the surface by allowing it to dissolve in the water. And so this reaction up here, which maybe you know from the movie Fight Club, where they're adding lye to fat that they stole from a liposuction clinic so that they can make soap. So the mechanism for that is we have our OH, which comes from this NaOH, that's our hydroxyl, and we have then we have the ester bond, which is what binds our, so R1, R2. So this is what binds our, R2 is the fatty acid and R1 is the glycerin. And so this, once again, the more of that carbonyl chemistry, we end up having that go there. So then we have R1 going to oxygen, going to the carbon with that negative oxygen up there. This is our OH from the hydroxyl group, and then the R2, and this will come back down. The electrons will collapse back down, and their electrons are going to go to something that's more electronegative. So it can go here, and that will just be the back reaction, but sometimes it will also go to here. And so we end up with our R1, which was our glycerol, having, so it'll, grab up hydrogen from the solution. So you end up with your glycerol being freed up, and you end up with your fatty acid like this. Well, I said that this was not going to have this H on it, and that makes sense because if we do release this, then we end up with something like this, and this charge is less stable than a charge on this one, because this has that resonance that can stabilize it, where this does not. So whatever H might end up bound on this one is probably actually going to get stolen by this. This is a much stronger base. It's a much stronger nucleophile, and so that will end up getting the hydrogen, where this will end up with the charge on it. And so that's how soap works. All right, so just for quick review, I talked about how we have these fatty acids, and they can come as either saturated or unsaturated, and they can have more than one double bond, which would make them polyunsaturated. I talked about how there are different lengths, which has an effect on the melting point of the fatty acid, as well as these double bonds having an effect on the fatty acid. Oh, and one other thing that I forgot to talk about. So we can have these double bonds like this, where so as I described in an earlier video, we cannot have any sort of turning around this bond, because this double bond prevents any kind of rotation around this, and so we don't get any rotation. So what that means is we always have these bonds going like this, and when we have it going in the same direction like this, like what we have right here, where the bonds are coming off those N carbons in the same direction, this is called a cis double bond. And it is also possible that you have the opposite, where these bonds come off in opposite directions, which is called a trans double bond. And so if you're into politics, I guess you've probably heard of, cisgender and transgender, and cis means same direction. So with cisgender, it would be, you know, your gender and your sex are the same, I guess, and trans is different directions, just like transgender. Maybe you identify as something that as the gender that you weren't born with. So uh, I'm not saying you should believe one thing or the other here, but that's just the where the terminology comes from, is that that same and that different. So these are cis double bonds and these are trans double bond. And what happens is, so in over here we show our fatty acids having these cis double bonds everywhere, and those are the kinds of fatty acids that you find in your food. So the trans double bonds, if you have a fatty acid with a trans double bond, that's how you get a trans fat, which you've probably heard of, and trans fats are considered bad. And the reason they're considered bad is, as I will talk about more as we get into biochemistry, humans have enzymes that can actually break down these sorts of fatty acids with the cis double bond. We have enzymes that know how to work with these cis double bonds. We do not have enzymes that know how to work with these trans double bonds. And so if you eat trans fat, they don't really have it, our body can't do anything with them, so they just or they can't break it down anyway. And so that just ends up being fat that stays accumulated on your person. And so that's why trans fats are considered bad, is because we can't metabolize these. And so we end up just storing it as fat. And so yeah, if we have a trans fat, the molecule is going to look similar to a saturated fat, because it's going to have its double bond right there, for instance. Draw that a little straighter. So its shape is going to be just like a saturated fatty acid. That double bond is something that we as humans don't have the biochemistry to work with. All right, and so, like I said, we talked about the omega-3 fatty acids, where it's 3 away from the omega carbon. We talked about the formation of triglycerides and the difference between tri, di, and monoglycerides. Briefly covered the sphingolipids or sphingosine and its derivatives, and then we went over to cholesterol and talked about cholesterol and its various derivatives, and these are all molecules that we humans make using cholesterol. And so we know that cholesterol is a necessary part of our diet. You don't want too much of it, but we do need it in order to make all of these other things. I think I forgot to talk about the vitamin D, but you can kind of see how this could be derived from cholesterol. It has these 2 6-membered rings. It has this, which looks like it could easily become a 6-membered ring, as the 5-member ring, and so on. And then I talked about how the bile salt, which was made from the cholesterol, can be used to emulsify fat. I talked about how we can make soap out of fat. And I think, yeah, I had one other thing here that I forgot to mention, which it's called rancidification. So when fat becomes rancid, this is the mechanism for that. So what ends up happening is we lose this hydrogen it might be lost to some other molecule, and we end up with what's called a free radical. So you might have heard about that. So a free, as we talked about in the general chemistry stuff, single electrons, like in oxygen, we had the two pairs of electrons up here, and then we had these single electrons. So single electrons really want to get paired up with some other electron. And so when we have this, it's called a free radical. It's a single electron, and that wants really bad to pair up with something. And so what it will end up pairing up with is oxygen in the atmosphere. So this, and when you're doing free radical reactions, instead of doing a double-headed arrow, since we're only talking about one electron, we use a single-headed arrow, and then this oxygen, this double oxygen here, will become attached to your fatty acid chain, and then that will become bound to some hydrogen, and this L just means leaving group. So that it just leaves, and that ends up being another free radical, which will then react with something else, which is why free radicals are not something you want, because they really want to pair up with something, so they like to react with things really strongly, and because you end up with this sort of odd electron out, you just end up passing it along, and you get these chain reactions where it's just a daisy chain of one thing happening, and then you still have this free electron, so that reacts with something else, which will be left with a free electron, and you just have this large cascade of reactions going on. But rancidification, when fat becomes rancid, you end up with this double O bond on it, which, if we have R here, we have O, O, then H, and this is called a peroxide group. So you may have heard of hydrogen peroxide, which is this, except instead of R, we have an H like this. And the reason that peroxides are bad news is these can fairly easily become free radicals. So you can end up with one electron going here and one going here. Oops. Yeah, so one going there and one going there, so that you end up with your R with a free radical, and you end up with another free radical like that. So these peroxides can be pretty dangerous, and when you use hydrogen peroxide, you're actually using the dangerousness of it to kill bacteria, like if you get a wound or something. So that's what a peroxide is for. Okay, so that is rancidification. I've kind of gone over everything. I've reviewed it. And I think that is where I will end this video. So I will see you next time when I cover amino acids and proteins.